Welcome to the 6th lab in Physics 187. In last week's lab, we measured the speed of the stars in arc seconds per year as they moved across our field of view. This week, we're going to use a technique that allows us to determine how fast the stars are moving either away from us or toward us. One of the problems we have with measuring the speed of stars is that when we look at the celestial sphere, we have no depth perception. And so while I can get a sense of how fast something is moving by noting how you might move closer or farther away from me, as I'm doing with this camera, for stars we really don't have that opportunity. And so what we need to do is we need to find some other technique that allows us to get a sense of how fast those stars are moving. Fortunately, we have a technique that allows us to do that, and that's a phenomenon in physics called the Doppler effect. The Doppler effect is just a phenomena that applies to moving bodies that may be emitting some type of wave. In the case of stars, they're emitting light. And by looking at the light coming from those stars and noticing by how much the wavelength of that light has changed compared to what it would be if the star was standing still, we can actually get a value for how fast that star is moving. We use a fairly simple equation to help us understand this. We know that if we consider how much the wavelength of a star has changed, or the light from the star has changed, we use this Greek symbol lambda right here to represent the wavelength, and this triangle represents change. If we look at the change in the wavelength divided by the original wavelength of the light, that's about equal to the speed of the star divided by the speed of light. And so if we want to find the speed of a star, all we really need to do is take this fractional change in wavelength and multiply by the speed of light. The speed of light is in your lab manual. We'll be finding the speed in meters per second, and so we'll use the speed of light as 3 times 10 to the 8th meters per second. We'll also be using wavelengths in the hydrogen spectra, and so the wavelengths for those will range from the low 400 nanometers up to the mid 600 nanometers. And we'll look at those specific wavelengths when we look at these individual stars. Let's go ahead and take a look at the lab and what you will see when you will open up the lab manual. You'll get a view of the sky, and you will have a crosshairs in the middle that will represent the orientation of your telescope. The first thing you want to do is you want to change the number of stars for which you'll be measuring the speed down to 10. Take a quick count. If by some chance you don't find 10 stars in the sky and you only have 9, that will be fine. Just make a note of that when you turn in your lab manual. In order to be able to measure the light from the star, what I need to do is I need to make sure that this star is centered on the crosshairs, and so I'll just simply realign the telescope by using the controls on the side. Note you're moving the stars, not the telescope, or you'll appear to be moving the stars, not the telescope. Once I have a star centered in, notice down here on the bottom, you will observe some spectral lines. You have 4 spectral lines, which you may not be able to see in this particular video, but there's a violet, a second violet, a green, and a red. If we click on one of these lines, it will expand the line so that you can see that the light is actually Doppler shifted, the wavelength has changed. The green line that you see up here on the top is the reference line. This is where the light would be located if the star was not moving. The light you see on the bottom is the light from the star, and you can see that it's been shifted over. In order to find the speed of the star, what you'll need to do is you'll need to find the Doppler shift for the wavelengths for each of these stars. You'll count over 1, 2, 3, 4, about 4 not quite 4.3, about 4.25 squares. Notice there's a scale here on the bottom that tells you that each one of those squares is worth 0.015 nanometers. So by counting the number of squares and multiplying by the scale, you'll get a sense by how much that wavelength has shifted. For each of these 10 stars, you will need to measure the Doppler shift for each of the 4 wavelengths that are produced by hydrogen. So you'll have the green at 486, you'll have one of the violet at 410, you'll have the other violet at 434, and you'll have the red at 656. Okay. To help you do these calculations, you'll be provided with a spreadsheet. Let's look at what happens in the spreadsheet. What you're simply entering in all of these boxes would be the number of squares that you have measured for each of those different colored lines. If I go ahead and enter in sample calculation, let me just assume that violet line was separated by 2 divisions. Notice what happens. It takes that number of divisions, multiplies it by the scale to get the actual change in wavelength. And then in this particular box right here, it will calculate the fractional change in wavelength by taking 0.03 and dividing by the original wavelength. We can look at the formulas in those cells. Notice in this cell, it multiplies the number of squares times the scale right up here. And in this cell, it takes that particular value and divides by the original wavelength up here. The same will happen for all of the other colors. You'll just go ahead and count the number of divisions and the calculations will be done for you. When you submit your lab report, I would like you to provide me with one sample calculation for one star. That takes me through the entire process of counting the number of squares, of using that to find the change in wavelength, finding the fractional change in wavelength for each of those wavelengths. Now, one of the things we do to minimize the error is to go ahead and take an average value of each of those fractional changes, right? So you might make a mistake on one, but it's less likely that you'll make a mistake on all 4. And by averaging together, we minimize any measurement errors that you might have made. And so we find the average fractional change in wavelength. The way you'd find any average, you'd add up the 4 values and you divide by 4. And then to find the speed of that particular star, we go ahead and use the equation that I provided for you on the board. We take that fractional change in wavelength. We take that fractional change in wavelength, right, C8, which is this value from right here, and multiply it by the speed of light. You will do this for all 10 stars that you have in your field of view, and check those answers for those stars. So you'll enter the number of the star. You will enter the Doppler shift in nanometers, right? So be very careful. This isn't the number of squares. This is the actual Doppler shift. The fractional Doppler shift is the ratio of the change in wavelength to the wavelength. Your average, and then your speed. Enter the number of the star. You'll need to check this for all of the stars. You can do a screen capture of each of these windows and shrink them down, so you should be able to fit all 10 of these screenshots onto a single piece of paper. This then will give us sort of the last step. With last week's lab and this week's lab, we can now come up with a way of measuring the speed of those stars. If you have any questions with this week's lab, please email me. Good luck.